A cosmic object 100 times bigger than anything we've ever tracked just entered our solar system, and it looks like it's hunting a smaller, equally strange visitor that arrived just weeks before. On September 12, 2025, astronomers witnessed an impossibility. Two massive, anomalous bodies arriving from opposite ends of the galaxy, set to rendezvous near the Sun. The odds are non-existent, and the evidence points not to a comet, but to a fortress. Let's explore this together. SWAN's dramatic arrival. What does it look like when the impossible streaks across the sky? On September 12, 2025, we found out. The SWAN instrument, a solar wind anisotropy sensor aboard the SOHO spacecraft, flagged a new object blazing a path through the inner solar system. The first data sets, analyzed by teams led by SOHO project scientist Bernhard Fleck, were staggering. The object possessed a tail stretching nearly 2.5 degrees across the sky, about 5 times the width of a full moon. To put that in perspective, a tail of that magnitude suggests a hydrogen outgassing rate hundreds of times greater than a typical long-period comet. Its initial brightness was clocked at magnitude 7.4, luminous enough to be seen with backyard telescopes from a distance of over 150 million kilometers. This wasn't some faint smudge, this was a spectacle. News ignited across astronomy networks, and just 2 days later an amateur observer captured a jaw-dropping image showing a streak so immense it barely fit the camera's frame. It was too big, too bright, and its trajectory was already looking far too precise. The raw energy output required to generate such a visible display at that distance was the first red flag that this was something entirely new. Official recognition and growing mystery. How do you classify something that breaks all the rules? By September 13th, the Minor Planet Center, where figures like the late, great Gareth V. Williams once vetted such discoveries, made it official. The object was designated C2025 R2 or SWAN, acknowledging the instrument that found it. That official stamp kicked off a global frenzy. Its initial orbital eccentricity was calculated at over 0.999. Confirming it as a long-period visitor on a path that would take millennia to repeat. The sheer size and luminosity created a wave of disbelief. Veteran astronomers had to reach back to the legendary comet Hale-Bopp of 1997, a comet with a nucleus estimated at 60 kilometers in diameter, to find a worthy comparison. SWAN, however, was already outshining Hale-Bopp at a similar distance from the Sun. It was slicing through the constellation Virgo, growing brighter as it approached its perihelion of roughly 1.0 AU, the same distance as Earth is from the Sun. The question shifted from what it was, to why it had arrived right now with such perfect timing. The numbers didn't just suggest a large object, they hinted at an impossibly active one. The cosmic coincidence. Some things are so unlikely they stop looking like a coincidence. See 2025. R2 SWAN is not the only strange visitor this October. Days before, another object, 3I Atlas, was already inbound from a completely different part of the sky. Imagine a celestial map. SWAN's path traces back from Aquarius, while Atlas entered from the direction of Sagittarius. Yet both are set to reach their closest pass by the Sun within the same 10-day window. For Atlas, that's October 17th at a distance of 1.36 AU. For SWAN, it's just 3 days later around October 20th, at a much closer 1.0 AU. Their perihelion points are separated by only about 50 million kilometers, closer than Mars ever gets to Earth. The geometry is what's truly stunning. Both are on steeply inclined orbits, with SWAN's path tilted more than 60 degrees and Atlas nearly 90 degrees to the ecliptic plane. As orbital dynamicist Paul Wiegert would tell you, the statistical probability of this kind of synchronized arrival from such different trajectories is infinitesimally small. It's a corridor in space-time that seems to have been deliberately targeted. This is not random chance, it is a rendezvous. Atlas breaks the rules. So, what do you do when an object's very existence, just flat out violates physics? 3I/Atlas, discovered by the University of Hawaii's Asteroid Terrestrial Impact Last Alert System Survey, which was headed by Larry Deneau, first got attention for its unusual composition. Early spectrographs showed a body dominated by nickel with almost no iron at all. This directly contradicts our knowledge of asteroids, which, nearly always feature iron-nickel alloys in really predictable ratios. But the anomalies didn't stop there. Instead of water vapor, Atlas's coma was pumping out carbon dioxide, with its 4.3 micron spectral line dominating every single reading. But the real smoking gun was its movement. Observers logged 3 distinct, non-gravitational accelerations, on July 29, August 14, and August 30. These weren't smooth pushes, they were sharp bursts, delivering a delta V of several meters per second each time. The behavior was so precise it was actually dubbed thrust mix modulation, which honestly implies a controlled engine burn that was adjusting its composition output. The data held up across multiple observatories, painting a pretty clear picture. This thing was under its own power and on a mission. The physics, well, simply left no other room for interpretation. SWAN, the Fortress. If Atlas is a nimble drone, then SWAN is basically a battleship. The scale of C/2025 R2 is honestly hard to comprehend, but it's the data that paints a really radical picture, one that has driven speculators like Harvard's Avi Loeb to consider similar theories for other objects. It all began with reflectance data. SWAN's core has an albedo, or reflectivity, way higher than a typical dark comet nucleus, actually matching the signature of polished metal. Some analysts argue it fits a nickel-cobalt blend, which is an alloy used for its immense strength. Then came reports of this silvery halo around the nucleus, an anomaly some folks interpret as a plasma envelope, or maybe even an electromagnetic shield. This is where it earned the nickname, the Fortress. Unlike Atlas, SWAN appears steady and, well, invulnerable, refusing to fragment as it gets closer to the sun. Even its tail shows evidence of micro-thrusts, tiny rhythmic pulses at a consistent frequency that just defy natural outgassing. Add in its 22,554-year orbit, and you have an object that appears to be ancient, armored, and, yeah, on a deliberate powered course. It isn't just passing through, it's arriving. Mission theories. When a 1 in a trillion coincidence happens, you really have to consider that it wasn't a coincidence at all. The timing, the geometry, and all this anomalous behavior have fueled a bunch of mission theories. One is a scheduled refueling run, which actually fits with concepts of advanced astroengineering proposed by physicists like Freeman Dyson. A more unsettling theory is an intervention, a rendezvous to neutralize a malfunctioning unit. The estimated power levels, Atlas at 10 gigawatts and SWAN at a staggering 10,000 gigawatts, suggest energy reserves needed for active maneuvering, not just passive drifting. There's also the audit chain scenario that 1I/Oumuamua in 2017 and 2I/Borisov in 2019, both on hyperbolic trajectories, were scouts. Atlas was a more advanced follow-up, and now SWAN is the main event. In every single case, the sun is the rendezvous point, the most powerful energy source in the entire system. The evidence honestly forces us to ask, if this is a mission, what is the objective? These aren't just rocks, they're actors on a cosmic stage. Ancient connections. An orbit of 22,554 years is, well, a link to a different chapter of human history. The last time SWAN would have passed was around 20,000 BCE, right at the peak of the last glacial maximum. Now, this is where the story connects to Göbekli Tepe, a site in Turkey built around 9500 BCE. Researcher Martin Sweatman has proposed a pretty controversial theory that its pillars are actually an astronomical observatory, recording a cataclysmic comet impact that triggered the Younger Dryas climate shift. He argues that Pillar 43 specifically tracks a long-period celestial object. But mainstream archaeologists, including the site's original lead excavator Klaus Schmidt, strongly disputed this, maintaining the carvings are symbolic. Still, the timing is, hard to ignore. If SWAN is on a recurring path, its last visit coincided with a transformative period for humanity. Whether that is a coincidence or a clue remains a fiercely debated question. It adds a layer of mythic resonance to an unbelievable event, suggesting we may have seen this visitor before. The blackout window. Just when things are about to get interesting, the curtains are being drawn. From October 8th to 18th, every major ground-based observatory from the Very Large Telescope in Chile to the Keck Observatory in Hawaii is effectively blind. This solar conjunction is predictable. What isn't normal is the alleged response. According to inside sources, memos from U.S. Space Command and the ESA have directed teams to suspend all imaging. The official rationale is to protect sensitive optics from the sun's glare. But that doesn't explain why radar facilities like Arecibo's successor, which are immune to solar glare, would also be ordered to stand down. This specific detail makes the official story fall apart. Proposals for alternative observation methods have reportedly been denied, and data requests have been delayed. Several telescope allocation reviewers describe explicit orders to avoid public statements. The result is a forced information vacuum at the most critical moment. Underground resistance. When the official channels go dark, the people build their own. The blackout order may have silenced major observatories, but it ignited a firestorm in the amateur and independent astronomy communities. Veteran tracker Bill Gray put out a call to arms across public forums. Keep your scopes on the sky, log everything, and share the raw data on open-source servers. A distributed web of astronomers with powerful 14 and 20-inch telescopes answered. Collectives like the Ibero Tracker Group in Europe began pooling their photometric and astrometric data feeds. Leaks suggest plans to use radio telescopes to pierce the solar glare. This grassroots effort has become the only real-time source for what might happen during the blackout. It's a powerful narrative of decentralized science, a global network ensuring no data disappears. When SWAN and Atlas re-emerge, the first images confirming their post-perihelion behavior might come from a garage, not a government lab. This has become a testament to citizen science. Power estimates and implications. Let's talk about the energy required to make these objects move. Atlas's accelerations required a power source of around 10 gigawatts, the output of 10 large nuclear power plants, but that is dwarfed by SWAN. Based on its luminosity, its suspected micro-thrusts, and the energy needed for a plasma shield, the Fortress could be wielding something close to 10,000 gigawatts. That is more raw output than the entire power grid of planet Earth combined. On the Kardashev scale, a civilization capable of controlling energy on this level is approaching Type 1 status. These are not trivial anomalies. These figures are the hardest evidence to dismiss as natural phenomena. They move the conversation from astronomy into astroengineering and contact theory. The sheer physics involves screams that we are dealing with a technology far beyond our own, powered by a source we can't yet comprehend. This is the bottom line that makes the engineered object hypothesis so compellingly logical. The facts are as clear as they are unnerving. Two anomalous objects defying all statistical odds have entered our solar system on a synchronized path. One appears to be a powered drone, the other an armored fortress. They are scheduled for a close encounter during a 10-day window, where they will be conveniently hidden from our best telescopes by the sun, accompanied by an official, top-down order for radio silence. This has forced the search for answers into the hands of a global network of citizen scientists. Are we witnessing a cosmic accident, a pre-planned mission, or something else entirely? Whatever the truth is, we are about to find out. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching Sci and Why. When CERN's Large Hadron Collider smashed protons together at unprecedented energies, scientists weren't just hunting for new particles. They were searching for something far more extraordinary: microscopic black holes. These quantum-scale phenomena, predicted by cutting-edge theories involving extra dimensions, could revolutionize our understanding of gravity and space-time itself. Today on Sci and Why, we're unveiling what really happened when the world's most powerful particle accelerator went hunting for the universe's most mysterious objects. The quest for quantum black holes. CERN's scientists embarked on one of the most ambitious experiments in physics history, deliberately trying to create black holes in a laboratory setting. The search for microscopic black holes at CERN represents a fascinating intersection of theoretical physics and experimental reality. Unlike the massive black holes found in space, these quantum black holes would be incredibly tiny, existing at subatomic scales and lasting for mere fractions of a second. The CMS experiment at CERN's Large Hadron Collider has been actively searching for these phenomena since the facility's early operations. According to CERN's official documentation, some theoretical models suggest that microscopic black holes could form when particles collide with sufficient energy, particularly if our universe contains extra spatial dimensions beyond the familiar three. These theories, including the Arkani-Hamed-Dimopoulos-Dvali model and the Randall-Sundrum scenario, propose that gravity might be much stronger at quantum scales than previously thought. The LHC's proton-proton collisions at energies up to 13 TeV create conditions where, according to these models, space-time itself could briefly collapse into microscopic black holes. If formed, these quantum objects would immediately evaporate through Hawking radiation, producing distinctive particle signatures that CERN's sophisticated detectors could potentially observe. The theoretical foundation. The possibility of creating black holes in particle accelerators stems from revolutionary theories that suggest our universe has hidden dimensions we can't perceive. The theoretical framework for microscopic black hole production relies on models involving extraspatial dimensions. In standard four-dimensional physics, creating a black hole would require concentrating energy equivalent to about 10 to the 19th GeV, far beyond any human-made technology. However, theories like the ADD model propose that gravity might propagate through additional dimensions, while other forces remain confined to our familiar three-dimensional space. This would effectively lower the energy threshold for black hole formation to potentially just a few TeV, precisely within the LHC's operational range. Dr. Lisa Randall and Raman Sundram developed influential models suggesting that if extra dimensions exist, the fundamental scale of gravity could be much lower than previously thought. These theories emerged to solve the hierarchy problem, explaining why gravity appears so much weaker than other fundamental forces. If correct, when protons collide at nearly light speed in the LHC, they could concentrate enough energy within a tiny region to exceed the Schwarzschild radius, causing spacetime to collapse into a microscopic black hole. The mathematics behind these theories is elegant but complex, requiring sophisticated computational models to predict observable signatures. CERN's experimental search. Armed with the world's most sensitive particle detectors, CERN scientists began their systematic hunt for evidence of microscopic black hole creation. The CMS experiment at CERN has conducted extensive searches for microscopic black hole signatures in high-energy proton-proton collisions. Using data collected during the LHC's operations at 7 TeV center of mass energy, researchers analyzed collision events looking for the distinctive particle sprays that would result from black hole evaporation. According to CERN's published results, if microscopic black holes were produced, they would evaporate almost instantaneously through Hawking radiation, creating characteristic patterns of subatomic particles detectable by the CMS detector surrounding the collision point. The search methodology involved examining invariant mass spectra of particle jets, looking for anomalies that couldn't be explained by standard particle physics. Scientists used sophisticated Monte Carlo simulations to model expected black hole signatures, comparing these predictions against actual collision data. The ATLAS experiment has also conducted similar searches, analyzing electron plus jet and muon plus jet invariant mass spectra with 140 inverse femtobarns of collected data. These experiments represent some of the most sensitive searches ever conducted for quantum gravitational effects, pushing the boundaries of what's experimentally accessible in fundamental physics. The surprising results. After analyzing millions of particle collisions, CERN's results challenged expectations and honestly, revealed something unexpected about the nature of reality. The experimental searches conducted by both the CMS and ATLAS experiments have yielded some pretty fascinating results. No direct evidence for microscopic black hole production has been found in the energy ranges examined so far. The CMS experiment's analysis of 7 tera-electron-volt collisions ruled out the existence of microscopic black holes, up to masses of 3.5 to 4.5 tera-electron-volts, for various theoretical models. More recently, the ATLAS experiment search using 13 tera-electron-volt collision data set even more stringent limits, excluding quantum black hole production up to 9.2 tera-electron-volts in the Arkani-Hamed-Dimopoulos-Dvali model, and 6.8 tera-electron-volts in the Randall-Sundram model. These non-observations are actually scientifically significant because they constrain the parameters of extra-dimensional theories. The absence of black hole signatures at these energy scales suggests that either extra dimensions don't exist as these models predict, or the fundamental scale of gravity is higher than theorized. However, these results don't definitively rule out microscopic black holes. They simply push the energy threshold higher, potentially requiring future collider experiments with even greater energies to test these theories conclusively. Safety considerations and public concerns. The prospect of creating black holes on Earth sparked widespread public concern, forcing scientists to address some pretty fundamental questions about experimental safety. Public fears about CERN creating dangerous black holes have persisted since the LHC's inception, and honestly, they've been amplified by popular culture and social media speculation. CERN has consistently addressed these concerns through comprehensive safety assessments and public education. According to CERN's official safety documentation, any microscopic black holes produced would be perfectly safe because they would evaporate almost instantaneously through Hawking radiation. The fundamental safety argument relies on cosmic ray interactions. High-energy particles from space constantly bombard Earth's atmosphere with energies far exceeding the LHC's capabilities, up to 10 to the 20th electron volts. If dangerous black holes could be produced at LHC energies, cosmic rays would have already created them throughout Earth's 4.5 billion-year history. Dr. John Ellis and other CERN physicists have emphasized that even hypothetically stable microscopic black holes would be harmless because they would interact so weakly with ordinary matter that they would pass through Earth without effect. The LHC Safety Assessment Group concluded that the experiments pose no conceivable danger, with multiple independent reviews confirming these findings. Hawking radiation and quantum effects. Stephen Hawking's groundbreaking theory predicts that microscopic black holes wouldn't grow and consume matter. Instead, they would explode in bursts of quantum radiation. Hawking radiation theory, developed by Stephen Hawking in the 1970s, fundamentally changed our understanding of black hole behavior. According to this theory, black holes aren't completely black but emit radiation through quantum effects at their event horizons. For microscopic black holes, this process would be extraordinarily rapid. Objects with masses comparable to elementary particles would evaporate in approximately 10 to the minus 27 seconds. The smaller the black hole, the more intense its Hawking radiation and the faster it evaporates. This creates a natural safety mechanism. Any microscopic black holes produced at CERN would immediately decay into standard model particles before they could interact with surrounding matter. The evaporation process would produce a distinctive spray of particles including photons, electrons, muons and quarks, creating detectable signatures in CERN's instruments. Theoretical calculations suggest that the temperature of Hawking radiation from a microscopic black hole would be incredibly high, potentially reaching 10 to the 17th Kelvin. This extreme temperature would cause the black hole to radiate away its entire mass almost instantaneously, making it impossible for such objects to grow or pose any danger to their surroundings. Implications for extra dimensions. The search for microscopic black holes at CERN represents honestly humanity's first experimental probe into the possibility that our universe contains hidden spatial dimensions. The theoretical models predicting microscopic black hole production are, intimately connected to theories of extra dimensions. These models suggest that our familiar three-dimensional space might actually be embedded in a higher dimensional reality, with gravity able to propagate through these additional dimensions, while other forces remain confined to our observable space. The ADD model, which was developed by Nima Arkani Hamed, Savas Dimopoulos, and Gia Dvali, proposes that gravity appears weak because it spreads out through large extra dimensions. Meanwhile, the Randall-Sundrum model suggests that we live on a three-dimensional brain within a five-dimensional space, with gravity concentrated near our brain by the geometry of space-time itself. CERN's experimental limits on black hole production provide, crucial constraints on these theories. The absence of black hole signatures at current energy scales suggests that if extra dimensions exist, they must be smaller or configured differently than some models predict. These results represent the first experimental tests of quantum gravity theories, providing invaluable data for theoretical physicists working to understand the fundamental structure of spacetime and the unification of quantum mechanics with general relativity. Advanced detection methods. CERN's scientists, have developed some truly revolutionary detection techniques to identify the fleeting signatures of microscopic black holes among millions of particle collisions. The search for these tiny black holes required developing really sophisticated analysis techniques to distinguish potential black hole signatures from ordinary particle physics processes. The CMS and ATLAS detectors use these multi-layered systems, silicon trackers, electromagnetic calorimeters, and muon chambers, to reconstruct particle trajectories and energies with, honestly, extraordinary precision. Scientists have also developed specialized algorithms to identify the high multiplicity particle jets that would result from black hole evaporation, looking for events with unusually large numbers of particles produced in spherically symmetric patterns. On top of that, machine learning techniques have been employed to analyze vast datasets, training neural networks to recognize potential black hole signatures among the billions of collision events recorded. The analysis focuses on invariant mass distributions, searching for resonances or anomalies that just can't be explained by standard model processes. Researchers use Monte Carlo simulations, which incorporate various black hole models, to predict expected signatures, then compare these predictions against real data using statistical methods. The detection challenge is immense. Potential black hole events would be extremely rare, requiring analysis of petabytes of collision data to identify possible candidates among overwhelming backgrounds of ordinary particle interactions. Future prospects and higher energies. As CERN prepares for even more powerful experiments, the search for microscopic black holes is, well, entering a new phase with unprecedented energy scales. The high-luminosity LHC upgrade, which is scheduled for completion in the late 2020s, will actually increase collision rates by a factor of 10, providing vastly more data for rare event searches. This enhanced capability could push the search for microscopic black holes to higher mass scales, potentially reaching the thresholds predicted by some extra-dimensional models. Looking ahead, future collider projects, including the proposed future circular collider, with energies up to 100 TeV, would provide even more sensitive probes of quantum gravity effects. The increased energy and luminosity would allow scientists to explore black hole production at mass scales up to 50 TeV or higher, definitively testing many theoretical predictions. Advanced detector technologies under development like improved calorimetry and faster data acquisition systems will enhance the sensitivity to black hole signatures. Theoretical work is also continuing to refine predictions, with new models suggesting alternative signatures that might be more easily detectable. Really, the combination of higher energies, improved detectors, and more sophisticated analysis techniques may finally provide the experimental breakthrough needed to either discover microscopic black holes or definitively rule out their production at collider energies. The broader impact on physics. Whether CERN finds microscopic black holes or not, the search itself is, honestly, revolutionizing our understanding of fundamental physics and the nature of reality. The quest for microscopic black holes at CERN represents more than just hunting for exotic objects. It's really testing the very foundations of our understanding of space-time, gravity, and quantum mechanics. The experimental limits already established have constrained theories of extra dimensions and quantum gravity, forcing theorists to refine their models and develop new approaches to unifying fundamental forces. The sophisticated detection methods developed for black hole searches have advanced experimental techniques across particle physics, improving our ability to discover other new phenomena. The safety analyses conducted for these experiments have also deepened our understanding of cosmic ray interactions and astrophysical processes. Even negative results provide valuable scientific information, ruling out certain theoretical possibilities and guiding future research directions. The interdisciplinary nature of this research has fostered collaboration between particle physicists, cosmologists, and theoretical physicists, leading to new insights about the universe's structure. As CERN continues pushing the boundaries of experimental physics, the search for microscopic black holes remains a powerful probe of reality's deepest mysteries, potentially revealing whether our universe truly contains hidden dimensions and whether quantum mechanics and gravity can be unified into a single theoretical framework. CERN's search for microscopic black holes represents humanity's boldest attempt to probe the fundamental nature of reality itself. While no black holes have been detected yet, the journey has revolutionized our understanding of physics and pushed the boundaries of what's experimentally possible. If you're fascinated by these cutting-edge discoveries and want to explore more mind-bending physics mysteries, hit that like button, share your thoughts in the comments, and subscribe to Sci and Y for more journeys into the universe's deepest secrets. Thanks for watching. Keep questioning reality. What if the most important discovery in human history appeared for just 1/30th of a second before the screen went black? On June 18, 2025, a NASA live feed tracking our third interstellar visitor, 3I Atlas, cut out at the exact moment a bizarre, unnatural-looking object flashed into view. The data is real, the blackout is confirmed, and the final frame is undeniable. Was it a glitch, a cover-up, or our first glimpse of alien technology? Let's delve into it. The initial discovery. How do you spot a messenger from another star system? You build a robotic sentinel to watch the entire sky. The Asteroid Terrestrial Impact Last Alert System, or ATLAS, is a network of telescopes designed to do just that. On July 1, 2025, Its automated systems flagged an object on a trajectory that immediately set it apart. Its path was hyperbolic, a clear sign it wasn't gravitationally bound to our sun. Much like Robert Warwick's 2017 discovery of Oumuamua, this was identified not by a single astronomer staring through an eyepiece, but by sophisticated software analyzing vast amounts of data. The object's extreme velocity and angle of entry confirmed it was a one-way visitor from the interstellar void. The Minor Planet Center, under the direction of Matthew Holman, quickly issued a circular designating it 3Y Atlas, confirming it as only the third such object ever detected. The global response was immediate and intense. With this early detection far earlier than Oumuamua was spotted, telescopes worldwide scrambled to observe the cosmic wanderer. This was a rare chance to study a piece of another solar system in unprecedented detail, a pristine time capsule from an unknown corner of the galaxy. The anomalous frame. What does a cosmic anomaly look like up close? At exactly 03:17 and 12 seconds UTC on that June night, just fractions of a second before the feed went dark, we got a shocking clue. The last recorded frame from the NASA feed shows what at first appears to be a standard cometary image, a dim nucleus, a hazy coma, and a faint tail. But in the lower left quadrant, something is fundamentally wrong. A razor-straight glint of light slices across the image. It's not a curve or an arc, it's a geometric edge, sharp and utterly at odds with the soft, natural contours of a comet. Independent astronomers inspired by the work of Karen Meach, who meticulously analyzed Oumuamua's strange light curve, immediately ran edge detection algorithms on the frame. The software flagged an almost perfectly straight line segment, measuring about 37 pixels from end to end. It reflected sunlight at a clean, sharp angle, unlike the diffused, scattered streaks expected from irregular comet dust. The light bounced as if from a polished, machined surface, not fractured ice or rock. It was a single, fleeting glimpse of something that, according to our understanding of cometary physics, simply shouldn't be there. Data verification. How do you prove a ghost in the machine is real? You check its digital fingerprints. In the world of astronomical data, this means cryptographic hashes and independent confirmation. Within minutes of the blackout on June 18, 2025, independent archivists in Australia, Germany, and the United States uploaded their own continuous packet captures of the NASA feed. Each file, stamped with the same 03:17 and 12 seconds UTC timestamp, came with a unique SHA-256 hash. When compared, every copy was identical, bit for bit. The hash for the Australian archive ending in 4F8D matched the German mirror and the original NASA relay. There was zero evidence of tampering. This is the new reality of citizen science, a decentralized backbone for data integrity that echoes the principles of transparency championed by figures like the late Carl Sagan. These archivists logged their actions in public ledgers, creating an airtight chain of custody. The anomaly appears in every single version of the feed, from the raw data streams to the compressed video. The data is clean, the archive is verified, and the mystery, preserved immutably, remains untouched by claims of digital alteration. Technical explanations. So why did the feed go black at that exact moment? The official line honestly points to mundane network logistics. NASA's live feeds are, well, a complex ballet of signals bounced between the tracking and data relay satellite system and the three main ground stations of the Deep Space Network in California, Spain, and Australia. According to engineers like Leslie Deutsch, a veteran of JPL who helped design parts of the DSN, dropouts are routine. When a satellite moves out of position or a signal is handed off between continents, you can get a brief interruption, often seen as a 2-second gray screen. These are called handover blanks, and they are logged with specific reason codes. They are usually just a consequence of orbital mechanics, a predictable part of space communication. This explanation, accounts for the blackout itself as a technical hiccup, but the timing is what troubles investigators. Was it just a one-in-a-million coincidence that this routine glitch occurred at the precise second a geometric anomaly, unprecedented in nature, appeared on screen? The official logs confirm the handover but can't explain the timing. Digital forensics. Can a simple glitch really look that perfect? Digital forensics teams, applying techniques similar to those used by experts like Hani Farid to analyze video authenticity, put the frame under a microscope. They found some compelling evidence for the skeptics. When they zoomed in, they noticed the sharp edge ran perfectly parallel to the borders of several 8 by 8 pixel macro blocks. That's a classic fingerprint of the MPEG video compression used for the feeds. NASA's algorithms slice each frame into a grid and can sometimes exaggerate faint lines. Then there's the issue of cosmic rays. Space is filled with high-energy particles that can slam into a camera's sensor, leaving a bright white streak for a single frame. This is a common artifact. It is entirely possible that a random cosmic ray hit was amplified by the video codec, creating the illusion of a solid edge. A double hit, a fleeting natural event made to look artificial by software. It's a highly plausible theory, one that relies on known phenomena. But does it fully explain the crispness and consistent brightness along the entire 37-pixel edge? That remains the heart of the debate. 3I Atlas background. What do we actually know about this interstellar traveler? Even without the anomalous glint, 3I Atlas is a cosmic outlier. Spectroscopic analysis from the James Webb Space Telescope's MIRI instrument, a device overseen by scientists like Gillian Wright, revealed it's unusually rich in carbon dioxide. The ratio of CO2 to water is about 8:1, far higher than comets from our own Oort cloud. This means its activity, the outgassing that creates its coma, is driven by frozen carbon dioxide turning to gas, not water ice. The coma itself is vast, stretching for hundreds of thousands of kilometers, with a dust cloud so dense it completely hides the nucleus. Based on its brightness, astronomers estimate the solid core is likely less than a kilometer across, comparable to 2I Borisov. Its early detection on July 1, 2025 by the Atlas survey gave scientists a crucial head start. It allowed them to watch this messenger from another star system come alive as it approached our sun, a process that has already yielded surprising new science about the chemistry of other planetary systems. Scientific scrutiny. So, how does a wild claim actually become an accepted fact in science? Well, it has to survive a pretty brutal gauntlet of scrutiny. Right now, the evidence for anything artificial on 3I Atlas sits, honestly, on the very first rung of the ladder of evidence. We're talking about a single anomaly in a single frame. To climb any higher, it really needs independent verification. On one side of the debate, you have cautious figures like astrophysicist Katie Mack, who would argue that we have to exhaust every possible natural and instrumental explanation before even considering an artificial one. On the other hand, there are thinkers like Harvard's Avi Loeb, who says that the discovery of Oumuamua already opened the door to considering technological origins for interstellar anomalies. For 3I Atlas, astronomers would need to see that same geometric edge with the Hubble, or maybe detect a strange spectral signature with ground-based scopes that matches a known alloy. Without multi-instrument confirmation, the scientific community will remain deeply skeptical, and honestly, rightly so. The edge remains a tantalizing but unproven candidate. 3 theories. So, where does this leave us? The debate is really fractured into 3 distinct paths. The first is a natural explanation based on cometary physics. As 3I Atlas heats up, jets of carbon dioxide erupt from its surface, which, honestly, can be strong enough to change its spin and break off shards of ice. The glint we saw could just be sunlight hitting the fresh, flat face of a newly fractured piece. The second path, which is actually favored by many, points to a technological illusion, a chance collision of a cosmic ray and a video compression artifact. But the third idea, while definitely the most speculative, stubbornly persists. What if the glint is from a machined surface? Proponents of this view, echoing the logic Avi Loeb applied to Oumuamua, suggest we could be looking at a probe or maybe even a piece of a larger craft. While Loeb's theories about Oumuamua were met with skepticism, astronomers like Darrell Seligman have since proposed that natural nitrogen icebergs could explain its behavior. But for 3I Atlas, no such elegant natural theory has yet emerged to explain the perfectly straight edge, which, honestly, keeps the artificial hypothesis uncomfortably on the table. Broader implications. An event like this, well, it ripples far beyond astronomy forums. When a NASA feed cuts out at such a critical moment, it really ignites a firestorm. Suddenly lawmakers are asking about data transparency protocols, and research teams are pushing for more open archives. It forces us to confront who actually controls the flow of information. It also galvanizes projects like the Galileo Project, co-founded by Avi Loeb, which is dedicated to actively searching for extraterrestrial technological signatures. Figures like Seth Shostak of the SETI Institute have long argued that any potential discovery would have profound societal implications. The 3I Atlas incident is, honestly, a perfect test case. It has raised the stakes, transforming a niche scientific question into a global conversation about our readiness for a discovery that could, change everything. The next time a feed from deep space drops, more eyes will be watching and more citizen archivists will be recording, ensuring the data remains in the public square. The search continues. The tantalizing mystery of 3I Atlas has already had a massive impact. It's injected a new sense of urgency into the search for interstellar objects. The Vera C. Rubin Observatory, under the leadership of director Zeljko Ivezic, is poised to discover dozens of these visitors every year as it begins its legacy survey of space and time in 2025. This will really transform the field from one of single, bizarre case studies into a robust statistical science. We will finally be able to determine if objects like 3I Atlas, with its strange composition and that anomalous glint, are common or exceedingly rare. Will we find more Oumuamuas and Atlases, or will they all look like the conventional comet 2I Borisov? The search is no longer just about finding rocks from other stars, it's about being prepared to find something we never expected. The next visitor is coming, and honestly it might just bring the answer with it, forcing us to finally confront the evidence, whatever it may be. The case of 3I Atlas remains unsolved. We have a single, provocative frame of data, verified and preserved, showing something that really defies easy explanation. We have a perfectly timed blackout that fuels speculation. And we have a set of competing theories, from a natural fracture to a cosmic glitch, to an artificial object. For now, it sits in digital limbo, a testament to how much we still have to learn about the universe. The only thing we know for sure is that the next visitor from the interstellar darkness is on its way, and this time, humanity will be watching more closely than ever before. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the mysteries of our cosmos. Thanks for watching Sci and Why. Interstellar space begins where the sun's influence fades, and the solar wind finally yields to the raw plasma of the Milky Way. Since 2017 we have confirmed just 3 visitors from that vast realm, the puzzling Oumuamua, herald of surprises, volatile comet Borisov, and now the outsized newcomer 3I Atlas. Each object is a priceless sample return mission delivered for free by nature, letting us probe chemistry, structure and age far beyond the planets. Tonight we collect every solid fact astronomers have pieced together about this latest cosmic ambassador. Beyond the heliopause, our interstellar visitors. The solar system's frontier is the heliopause, a shifting magnetic shell standing roughly 18 billion kilometers from the Sun. When Voyager 1 pierced that frontier in 2012, its plasma detector confirmed the long-predicted transition into interstellar space. Densities jumped, solar origin particles vanished, and cosmic ray counts spiked. Since then, terrestrial telescopes have reverse experienced the same crossing by spotting travelers arriving from the galaxy's dark sea. The odds are daunting. Dynamical models suggest only a few hundred-meter-scale bodies wander through the inner solar system each century. Yet modern wide-field surveys and continuous sky patrols have already netted 3 confirmed interstellar objects in just 8 years. Their hyperbolic speeds, inbound directions, and inability to be captured by solar gravity reveal origins that lie light-years away. Each new detection is therefore a planetary science windfall, a primitive shard of another star's debris disk, altered by eons of irradiation and micrometeoroid pummeling, finally falling within reach of Earth's spectrographs. As instrumental sensitivity grows, researchers expect a steady trickle of similar emissaries, gradually transforming Exotica into a statistically rich field of comparative planetology. The third visitor, 3I/ATLAS discovery. On June 2025, the twin Schmidt telescopes of the Asteroid Terrestrial Impact Last Alert System swept across the pre-dawn sky and registered an object moving too fast to be bound to the Sun. Alert messages flashed from Hawaii to South Africa and onto the Minor Planet Center, where the trajectory was confirmed within hours. Principal investigator Dr. Larry Deneau announced the team had netted 3Y Atlas, humanity's third verified interstellar wanderer. Early photometry implied a remarkable diameter between 10 and 20 kilometers, at least an order of magnitude larger than Oumuamua. That sheer size promised ample reflected sunlight for spectroscopy, galvanizing observatories on 5 continents to obtain time-critical data. Infrared spectra hinted at complex organics, millimeter-wave receivers searched for exotic volatiles, radar attempted shape reconstruction when geometry allowed. The discovery also demonstrated how automated pipelines, artificial intelligence vetting, and instantaneous worldwide coordination can turn a few faint pixels into an unprecedented international campaign within a single rotation of Earth. 3. Why Atlas thus became both a scientific target and a systems engineering triumph, showing that planetary defense infrastructure doubles as an accidental interstellar object early warning net. A hyperbolic journey at 58 kilometers. Trajectory solutions from JPL's Horizon system reveal 3I Atlas, racing along a hyperbolic trajectory with an inbound heliocentric speed of 58 kilometers per second. Calculations by Dr. Davide Farnochia show the path threads the orbits of Mars and Jupiter before the object slingshots back toward the galactic northwest, never to return. That excess velocity, nearly 3 times Earth's orbital speed, guarantees the visitor is unbound. No realistic gravitational interaction could capture it. Dynamical backtracing suggests 3Y Atlas last crossed the galactic plane 30 million years ago, and may have originated near the Carina Sagittarius spiral arm, though stellar encounter uncertainties are large. During its brief stay, it will feel weak but measurable tugs from planetary masses, allowing researchers to test N-body propagation codes under extreme boundary conditions. The rapid passage also forces astronomers into a sprint. Every observing window must be filled, sometimes with instruments never before aimed at the same target in a single night. Lessons learned from these coordination drills will feed directly into mission concepts such as ESA's Comet Interceptor, designed to launch quickly toward the next unpredictable celestial visitor. Brightness, rotation, and the 29-hour cycle. Time series photometry from the Nordic Optical Telescope reveals these quasi-periodic brightness swings of about 9/10 of a magnitude. This maps onto a rotation period of, well, around 29 hours. Data from the European Southern Observatory confirm an irregular, likely elongated body. Its long axis could exceed 9 kilometers, which is quite something. Now, if we invert the light curve, it suggests an axis ratio of approximately 3:1. This is comparable to Oumuamua's extreme proportions but on a much grander scale. The stability of this amplitude argues against the idea of loose rubble. Instead, it seems that 3I/Atlas might possess a cohesive monolithic core. This core is likely overlain by mantling regolith that accumulated during its galactic journey. Surface scattering models propose alternating patches of dark carbonized crust and brighter, possibly icy facets. These rotate into sunlight, driving the observed flux pattern. Continued monitoring aims to detect Yorp-induced spin-up or subtle precession. These phenomena could reveal internal density gradients. Polarimetric measurements planned for perihelion will test whether charged particle implantation or interstellar UV processing has glassified surface grains, a state never observed on indigenous comets. So, every rotational cycle opens a time-lapse window onto geological processes, operating far beyond the reach of any spacecraft. Coma, tail, and cometary activity. Solar heating at 1.5 astronomical units would normally trigger vigorous sublimation in an ice-rich nucleus. Yet, the Spitzer Space Telescope detected only a whisper of carbon monoxide and carbon dioxide. Lead investigator Dr. Colin Snodgrass suggests that cosmic ray gardening over millions of years may have sintered 3I/Atlas's upper meters into an insulating crust. This crust throttles volatile escape. Ground-based narrowband filters isolate a tenuous cyanogen halo, but production rates are nearly 2 orders of magnitude below those of Comet Borisov at a comparable distance. Radar attempts from Goldstone found no large dust grains, which is consistent with a surface depleted in friable material. The resulting weak coma and filamentary tail defy classical comet models. This suggests either an unusual primordial composition or extreme evolutionary processing. Should deeper layers ever fracture, a sudden jet could alter the trajectory. This would offer a real-time test of non-gravitational forces on an interstellar scale. Monitoring continues around the clock because even a modest outburst would provide precious gas for isotopic assays. This could potentially distinguish whether the body formed around a metal-poor population 2 star or within a young planet-forming disk more like our own nebular cradle. Oumuamua versus Borisov versus 3I/Atlas. Comparative planetology now has 3 data points beyond the heliopause. Oumuamua, flagged in 2017, was a cigar-shaped 200-meter object. It had perplexing non-gravitational acceleration but no detectable gas. Borisov erupted in 2019 with classical dust jets rich in carbon monoxide and hydrogen cyanide. It behaved like a solar system comet transplanted intact. In contrast, 3I/Atlas is 10 times larger than Oumuamua. It shows Borisov-style composition signatures only faintly and rotates slowly. Together, they outline a spectrum of possibilities: dormant shard, pristine comet, and massive, highly processed giant. Spectral slopes vary from Oumuamua's red, organic-rich hue to Borisov's more neutral tones. 3I/Atlas sits in between, pointing to mixed ice rock interiors masked by millennia of irradiation. Dynamically, all 3 arrived on different galactic vectors, indicating no shared parent system. The trio's collective diversity is reshaping models of planetesimal ejection. This implies that every maturing planetary system may fling out thousands of distinct fragments, icy, rocky, or hybrid, into interstellar exile. Future detections by Rubin Observatory will determine whether our current sample is typical or a statistical fluke driven by small number bias and selection effects. A 3 billion 11-year-old traveler. Isotope ratio modeling and cosmic ray exposure calculations, bracket 3I Atlas's formation epoch between 3 and 11 billion years, actually predating the Sun at the upper bound. High-energy proton bombardment gradually converts surface ice to complex refractory organics, which leads to the dark, reddish spectra seen in long-aged Kuiper Belt objects, and similar signatures adorn our visitor. Laboratory analogs produced under accelerator beams match the object's infrared absorption bands, supporting an ancient surface residency in the galactic field. Queen's University Belfast researcher Dr. Alan Fitzsimmons notes anomalously low crystalline ice features, implying the body spent little time near its natal star before ejection. Over giga-years, random supernova shocks, molecular cloud passages, and gravitational nudges from passing stars sculpted its current orbit, effectively sandblasting volatile layers while leaving mineral matrices intact. Each detected molecule, therefore, archives conditions from epochs otherwise inaccessible to observation. Studying such relics refines timelines for disk evolution, migration, and dynamical instability in alien solar systems. With only 3 interstellar samples so far, every additional chemical clue counts exponentially toward mapping the history of matter across the Milky Way. October 30th, perihelion and beyond. On October 30th, 2025, 3I/Atlas skimmed within just over 1 astronomical unit of the Sun, a geometry that placed it high in the northern skies. The James Webb Space Telescope devoted emergency directors discretionary time to obtain mid-infrared spectra, capturing silicate emission features rarely obtainable for interstellar bodies. Coordinated campaigns linked Subaru's visible light spectrograph, ALMA's sub-millimeter receivers, and amateur CCD networks into a single global array. The perihelion distance of 1.1 astronomical units allowed measurement of thermal inertia by tracking flux changes over the 29-hour rotation, constraining surface conductivity and porosity. Lead organizer Dr. Casey Lisi reports negligible change in gas production rates pre- and post-perihelion, bolstering the processed crust hypothesis. Hubble imaging after the closest approach detected a faint meteoroid trail, suggesting low-level dust loss perhaps triggered by microfractures. Precise astrometry during solar conjunction refined mass estimates via non-gravitational drift constraints, yielding a bulk density around 1.8 grams per cubic centimeter, denser than comet nuclei but lighter than stony asteroids. As 3I/Atlas recedes, radar pings and thermal mapping will continue until signal-to-noise evaporates, freezing an irreplaceable dataset for decades of post-mission analysis. Future observations and scientific opportunities. The forthcoming Vera C. Rubin Observatory promises to transform fleeting luck into routine science, with its legacy survey of space and time projected to discover dozens annually of interstellar objects as faint as 24th magnitude. Pipeline architect Dr. Michelle Bannister is configuring machine learning classifiers to flag hyperbolic motion within hours, enabling rapid response spectroscopic triage. Complementary radio searches at FAST and Meerkat will probe for OH masers produced when unprocessed ices meet sunlight, while ESA's proposed comet interceptor could be retargeted to chase the next sizable wanderer. Astrodynamicists are refining solar sail trajectories capable of 5 astronomical units per year departures, potentially intercepting outbound objects for close-up imaging or sample capture. Coupled with isotope microanalysis, such missions would revolutionize understanding of galactic chemical gradients, delivering ground truth unattainable by remote sensing alone. Moreover, interstellar grains embedded in Earth's atmosphere, first cataloged by NASA's Stardust mission, could be chemically matched to parent bodies like 3I/Atlas, linking macroscopic dynamics with microscopic composition. These interdisciplinary strategies will crystallize a new subfield, galactic small-body science, uniting astronomy, planetary geology, and heliophysics under a single question: how does matter move, evolve, and mingle across star systems? Conclusion and cosmic perspectives. In a single decade, humanity has advanced from 0 confirmed extrasolar planetesimals to detailed dossiers on 3, culminating in the colossal Robert Werik discovery lineage that now includes 3I/Atlas. Each arrival widens our chemical dictionary, tests dynamical models, and reminds us the solar system is porous, not isolated. The study of interstellar visitors transforms accidental alignments into deliberate natural experiments, revealing chemical signatures forged under alien suns. Ultimately, these bodies invite a profound, humbling realization. Planet formation, collision, and ejection are universal, scattering shards of distant worlds throughout the galaxy. As surveys grow sharper and propulsion methods bolder, future scientists will map these shards into a web of shared origins, dissolving the parochial notion that samples must be fetched by billion-dollar probes. Instead, the galaxy occasionally mails postcards in the form of ancient rocks, carrying isotopic clues and perhaps organic seeds. Harvesting their stories will redefine planetary science from a solar system discipline into a truly galactic understanding, linking every world, seen or unseen, into a dynamic, ever-exchanging community of matter. 3I/Atlas is already dimming, yet its data trove will inspire research for years. Whether colossal comet, irradiated asteroid, or something even stranger, it confirms our cosmos is alive with wanderers older than Earth itself. Which mystery intrigues you most? Its muted coma, ancient chemistry, or breakneck speed? Let us know in the comments. Like, share, and subscribe to Sci and Y for more journeys beyond the heliopause. Until next time, keep looking up and stay curious.